Welcome, everyone, to tonight's journey through the stars. You're listening to Science to Sleep By, where we travel through the mysteries of the universe in a way that both feeds your curiosity and gently guides your mind toward rest. Tonight, we take on an ambitious topic, the ultimate guide to absolutely everything in the universe. Together, we'll explore where everything began, how it works, and where it may be going. So, settle in, get comfortable, let your breathing slow, and allow the vastness of the cosmos to wash over you as we begin our exploration of absolutely everything. Close your eyes for a moment and imagine absolute nothingness. No stars, no galaxies, no planets, no air, no light, not even space itself. This is not just an empty room, not just a dark night sky, it is nothing at all. A void where even time has no meaning. Now imagine that void, a spark. Not a spark like fire, not a spark you could hold in your hand, but an unimaginable burst of energy that instantly expands, creating space and time as it unfolds. That moment is what scientists call the Big Bang, and it represents the birth of our universe, the origin of everything we know and everything we are. The Big Bang did not happen in space, because space itself was born in that instant. Before this event, there was no before in the way we normally think of it, because time itself only began with the birth of the universe. Around 13.8 billion years ago, the universe existed as something infinitely dense, infinitely hot, and infinitely small, a singularity beyond our comprehension. Then, in a fraction of a second, it began to expand, and it has never stopped expanding since. This expansion set into motion the processes that would eventually lead to galaxies, stars, planets, and life itself. At first, everything was pure energy. Matter, as we understand it, did not yet exist. The universe was a roiling soup of unimaginable heat, with particles forming and annihilating almost instantly. Quarks, the building blocks of protons and neutrons, appeared and vanished, until the universe cooled enough that they could bind together. In just the first few minutes after the Big Bang, the very first atomic nuclei, mostly hydrogen and helium, came into existence. These were the foundations for everything else. The seeds from which stars and galaxies would one day form. It is almost poetic to think that all of the heavier elements we know, carbon, oxygen, nitrogen, iron, even the calcium in your bones, were not present at the beginning. They had to be forged later inside the hearts of stars. But the lightest elements were born almost instantly, within minutes of creation. In a sense, hydrogen and helium are the original children of the universe, formed when everything was still young and wild, and they remain the most abundant elements across the cosmos. Even now. As the universe expanded, it cooled further. And about 380,000 years after the Big Bang, something profound happened. Light broke free. Before this point, the universe was opaque, filled with particles and photons colliding endlessly. But as things cooled, electrons were captured by nuclei, forming stable atoms. This process, called recombination, allowed light to travel freely through space for the first time. Today, we can still detect this ancient light as the cosmic microwave background, a faint glow that permeates the entire universe. It is like a photograph of the universe when it was still an infant, a record of its earliest days imprinted across the sky. For billions of years, scientists did not know this background existed. It wasn't until the mid-20th century that researchers stumbled upon it, almost by accident, while investigating strange static on a radio antenna. What they discovered was not noise from Earth, but a whisper from the universe's birth itself. To this day, the cosmic microwave background remains one of the most powerful pieces of evidence for the Big Bang theory, confirming that our universe truly had a beginning. After recombination, the universe entered what is sometimes called the cosmic dark ages. Stars had not yet formed, so the universe was filled with clouds of hydrogen and helium gas, cooling and expanding in the dark. Over hundreds of millions of years, tiny fluctuations in density began to grow under the influence of gravity. Where matter was just a little bit more concentrated, gravity pulled more matter in, eventually giving rise to the first stars and galaxies. These first stars were massive, short-lived giants, burning intensely and collapsing into supernova within only a few million years. They seeded the cosmos with heavier elements, preparing the way for new generations of stars, planets, and eventually life. What is perhaps most astonishing is that everything we see today, from the Milky Way to the smallest grain of dust floating in a sunbeam, can be traced back to that single point, that initial expansion. The Big Bang was not an explosion in space, it was an expansion of space itself. Imagine dots on the surface of a balloon. As the balloon inflates, the dots move away from each other not because they are moving through the surface, but because the surface itself is stretching. This is what the universe has been doing for 13.8 billion years. As vast as the universe appears today, it is still governed by the echoes of its birth. Even now, galaxies move apart as space stretches, carrying them with it. The expansion is not slowing down, but accelerating, driven by something we call dark energy, an invisible force that makes up about 70% of the universe, yet remains one of the greatest mysteries in science. When we look into the night sky, we are not just seeing stars. We are looking back through time, witnessing light that has traveled for billions of years to reach us. The farther we look, the closer we come to glimpsing the very beginning itself. For us here on Earth, it is difficult to comprehend the scales involved. 13.8 billion years is an almost impossible span of time, and the size of the observable universe, roughly 93 billion light-years across, is equally staggering. But science gives us the tools to understand these grand scales, and it gives us perspective on our place within them. Every atom in your body, every element that makes up your blood and bones, was once inside a star, and before that, inside the energy released at the dawn of time. You are literally a product of the universe's birth, a continuation of that first expansion, a living fragment of the cosmos that opened its eyes and became aware of itself. The Big Bang was not just the beginning of matter and energy, but also of laws of physics that govern everything we observe. The strength of gravity, the speed of light, the interactions of particles, all were set in motion at that initial moment. If any of these had been even slightly different, our universe might look nothing like it does today. Stars might never have formed, galaxies might never have coalesced, and life as we know it might never have appeared. The fact that we exist in a universe where all of these conditions align is a profound and humbling truth. So when we talk about the beginning of everything, we are not speaking only about distant galaxies or abstract physics. We are speaking about ourselves, our origins, and the deep connection that ties us to the cosmos. The Big Bang is not just a scientific theory, it is the story of how existence itself unfolded, the ultimate beginning that continues to ripple through time, shaping the stars above and the lives we live below. Imagine gazing up into the night sky, far away from the glow of city lights. You see countless stars, glittering like diamonds scattered across a vast black canvas. Yet even this breathtaking view is only a tiny fraction of the cosmos. Beyond those stars are galaxies, enormous collections of billions of stars, planets, nebulae, and dark matter, each one separated by incomprehensible distances. What is even more extraordinary is that these galaxies are not fixed in place. They are drifting, gliding, carried by the expansion of space itself, moving farther and farther apart as time stretches onward. The universe is not static. It is alive with motion, and that motion tells us a profound story about its origin and its destiny. For much of human history, people assumed the universe was eternal and unchanging. The stars overhead seemed constant, returning night after night, season after season. To early astronomers, the heavens looked like a great celestial dome, timeless and fixed. Even as telescopes revealed more details, the idea of a static universe remained strong. But in the 20th century, everything changed. In 1929, the American astronomer Edwin Hubble made a discovery that forever altered our understanding of the cosmos. By carefully studying the light from distant galaxies, he found that almost all of them appeared to be moving away from us. The farther away a galaxy was, the faster it seemed to be retreating. This discovery confirmed that the universe itself is expanding, carrying galaxies apart like dots on an inflating balloon. The key to Hubble's revelation lay in something called redshift. When light from a galaxy travels across space, the wavelength of that light is stretched as the universe expands. Just as the sound of a passing train changes pitch because of the Doppler effect, the light from galaxies shifts toward the red end of the spectrum if they are moving away. By measuring this redshift, Hubble was able to determine the speed at which galaxies were receding. What he found was astonishing. Not only were galaxies moving away, but their speed increased with distance. This relationship, known today as Hubble's law, became one of the cornerstones of modern cosmology. The implication was clear. If galaxies are moving apart now, then at some point in the distant past, they must have been closer together. If you run the expansion backward, all matter, energy, space, and time must converge to a single origin, the event we now call the Big Bang. Hubble's work gave us the evidence to understand that the universe had a beginning, and that its story is one of continual change. But the expansion of the universe is not like an explosion sending debris into empty space. Instead, space itself is stretching, and everything within it is being carried along. Imagine baking a loaf of raisin bread. As the dough rises, the raisins move farther apart, not because the raisins themselves are traveling, but because the dough between them is expanding. Galaxies behave much the same way. They are not speeding through space like rockets, but rather space itself is expanding and carrying them apart. For billions of years, this expansion has shaped the cosmos. In the early universe, matter was crowded together. Gravity pulled matter into clumps, and those clumps became galaxies. Over time, these galaxies clustered into larger structures, forming cosmic filaments and vast voids, creating a web-like pattern that spans the observable universe. When we map the cosmos today, we see that galaxies are not evenly scattered, but arranged in this intricate cosmic web. Each strand of the web contains clusters of galaxies, and each gap reveals enormous empty spaces where matter is scarce. This grand architecture is a direct consequence of expansion, gravity, and the flow of cosmic history. What makes the story even more intriguing is that expansion has not remained constant. For a long time, scientists assumed gravity would gradually slow the universe's growth. Galaxies, they thought, might eventually stop moving apart, perhaps even reversing direction in a great collapse known as the Big Crunch. But in the late 1990s, two independent teams of astronomers studying distant supernova discovered something unexpected. The expansion of the universe is not slowing down at all. It is speeding up. Galaxies are racing away from each other faster and faster, as though some mysterious force is pushing them apart. This unknown phenomenon is called dark energy. It makes up about 70% of the total energy of the universe, yet we know almost nothing about its nature. It does not emit light, it does not interact with matter in any detectable way, but its influence is unmistakable. It acts as a kind of anti-gravity, driving the acceleration of cosmic expansion. Its discovery was one of the greatest scientific surprises of the modern era, and it remains one of the deepest mysteries of physics. For us here on Earth, the expanding universe feels abstract, far removed from daily life, but its effects are woven into the fabric of reality itself. Every glance into the night sky is a glimpse into the past. Because light takes time to travel, when you look at the Andromeda galaxy, you see it as it was more than 2 million years ago. When you look at the faintest, most distant galaxies through powerful telescopes, you are looking billions of years into the past, seeing the universe as it was when it was young. The farther away something is, the more its light has been stretched by expansion, and the more ancient the snapshot becomes. In this way, the expansion of the universe is not just a concept, it is a time machine, carrying us back toward the beginning. Even within this grand expansion, galaxies themselves can move relative to one another. Gravity binds galaxies into clusters, and some galaxies even collide. In fact, our own Milky Way is on a slow-motion collision course with the Andromeda galaxy. In about 4 billion years, the two will merge into a single, larger galaxy. Despite the drama this suggests, the vast emptiness of space means that stars within these galaxies will almost never collide. Instead, the galaxies will swirl together, reshaping their structures into a new cosmic form. This kind of interaction is part of the larger dance of the universe, happening all across the cosmos, even as space itself expands. The expansion also tells us something about the universe's age. By measuring the rate of expansion, cosmologists can estimate how long the universe has been growing. Combined with other observations, this gives us the now widely accepted age of about 13.8 billion years. It is extraordinary to think that from the faint signals of distant galaxies, we can reconstruct not only the past, but also predict the universe's future. If expansion continues to accelerate, galaxies will eventually move so far apart that distant starlight will fade beyond our reach. Trillions of years from now, observers, if any remain, might see only their own galaxy, surrounded by darkness, unaware that countless others once existed. The cosmic web, the grandeur of billions of galaxies, could one day vanish from view, erased by expansion. It reminds us that our current time is special. We live in an era when the sky is full of galaxies, when we can still observe the echoes of the Big Bang, when the story of the universe is still legible to us. So, the expanding universe is not just a scientific fact, it is a reminder of impermanence, of change written across cosmic scales. Galaxies are not static jewels set into the heavens, but living, moving parts of a universe that is restless and dynamic. Every second, the cosmos stretches, and with it, the distances between galaxies grow. The universe is vast, but it is also alive with motion, and that motion began in the same moment that time itself began. When we say the universe is expanding, what we are really saying is that creation is still unfolding, that the story of the cosmos is still being written, one heartbeat of expansion at a time. When you step outside on a clear evening and look up at the night sky, what you're really seeing is the heartbeat of the universe. Those countless points of light that twinkle above you are not just distant decorations. They are stars, the engines that power galaxies, the furnaces that forge the elements, and the beacons that allow us to trace the story of the cosmos. Stars are the universe's way of transforming the simplest material, hydrogen and helium, into everything else, including the building blocks of life. Without stars, there would be no planets, no oceans, no forests, no people gazing up into the night sky. To understand stars is to understand the lifeblood of the universe. Stars begin their lives in clouds of gas and dust called nebulae. These vast regions can stretch for light years, appearing as luminous patches in the sky when illuminated by nearby stars. Within these clouds, gravity begins its quiet work, pulling particles together. At first, the motions are subtle, the gathering of dust and gas forming clumps. But as the clumps grow, gravity tightens its grip, drawing in more material. Over thousands, even millions of years, regions within the nebula collapse under their own weight, forming dense cores that heat up as pressure builds. It is within these hidden cradles that stars are born. As the gas compresses, the temperature at the center of the collapsing core rises. When it reaches millions of degrees, something extraordinary occurs. Nuclear fusion ignites. Hydrogen atoms are forced together so tightly that they fuse into helium, releasing enormous amounts of energy in the process. This energy pushes outward, balancing the inward pull of gravity. At that moment, a star is born, shining with a brilliance that can last for millions to billions of years. From the smallest red dwarfs to the largest blue giants, all stars share this essential balance between gravity pulling inward and fusion pushing outward. The light we see from a star is the outward expression of these nuclear reactions. Inside a star, the conditions are so extreme that matter exists in a plasma state, with atoms stripped of their electrons. In the sun's core, temperatures reach about 15 million degrees Celsius, and every second, 600 million tons of hydrogen are fused into helium. This process releases the energy that eventually radiates out into space, bathing planets in warmth and light. Without this constant fusion, the Earth would be a frozen, lifeless rock, adrift in the cold darkness of space. not all stars are the same. Their characteristics depend on their mass, and mass determines everything about a star's life, from how brightly it shines to how long it will last, and even how it will eventually die. Small stars, like red dwarfs, are faint and cool compared to larger stars, but they burn their fuel so slowly that they can live for trillions of years. Larger stars, like blue supergiants, blaze with immense brightness, but consume their hydrogen quickly, living only a few million years before burning out. Our sun falls somewhere in the middle, a yellow dwarf star with a lifespan of around 10 billion years, of which it is roughly halfway through. Over time, stars evolve. As hydrogen in the core is consumed, the delicate balance between gravity and pressure shifts. For a star like the Sun, this means that eventually, fusion will slow and the core will contract, while the outer layers expand. The star will swell into a red giant, its radius growing so large that it could engulf the inner planets of the solar system. After this phase, the Sun will shed its outer layers, leaving behind a glowing shell of gas called a planetary nebula. At the center will remain a dense, Earth-sized remnant known as a white dwarf, which will slowly cool and fade over billions of years. But for massive stars, the ending is far more dramatic. When their cores exhaust their fuel, gravity overwhelms the star's ability to support itself. The core collapses in a fraction of a second, triggering a titanic explosion called a supernova. In that brilliant, violent moment, the star unleashes more energy than our sun will emit in its entire lifetime. The outer layers are blasted into space, while the core may collapse into a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons, or even further into a black hole. A region where gravity is so intense that nothing, not even light, can escape. Supernova, though destructive, are essential for the universe. They are the cosmic forges that create and scatter the heavy elements. The oxygen you breathe, the iron in your blood, the gold in a wedding ring, all of it was formed in the heart of a massive star and released into space during its explosive death. Every atom heavier than helium was once inside a star. When you look at your hands, your bones, your breath, you are seeing star stuff. The famous words of Carl Sagan ring true. We are made of star dust, born from the remnants of long-dead stars that lived and died billions of years ago. Stars also shape the galaxies they inhabit. Their radiation sculpts the clouds of gas around them, triggering new generations of star formation. Their winds blow matter across vast distances, influencing the structure of entire regions of space. In their deaths, they enrich galaxies with the materials needed for planets and life. Without the cycles of star birth and death, the universe would be a much simpler place, beautiful, perhaps, but sterile and lifeless. The study of stars also provides us with the cosmic clock. By observing their brightness, color, and composition, astronomers can determine their ages, and in turn, the age of the galaxies they belong to. Variable stars, which change in brightness over time, act as distance markers, allowing us to measure how far away other galaxies are. Stars, then, are not just engines of creation. They are also tools of discovery, guiding us as we map the universe and trace its history. Our own sun, while ordinary compared to others, is extraordinary in its importance to us. Its steady light sustains life on Earth, drives weather patterns, powers photosynthesis, and provides the warmth needed for water to remain liquid. Without it, our planet would be a frozen wasteland. Its activity, from solar flares to sunspots, also reminds us of its power, as bursts of radiation and particles stream out into the solar system, shaping space weather that can affect satellites, power grids, and communications on Earth. The sun is not just a distant light in the sky, it is our star, our personal cosmic engine. When we think about stars, we are really thinking about time, creation, and connection. The light from the stars you see at night may have traveled for thousands, even millions of years to reach your eyes. To look at the night sky is to look back through time, to see the universe not as it is now, but as it once was. Some of the stars you admire may already be gone, their light still traveling across space, arriving at Earth long after their fires have extinguished. Each star is a story, a chapter in the grand narrative of the universe, a reminder that even in the vastness of space, creation and destruction are always intertwined. Stars are the cosmic engines, the relentless furnaces that drive everything else in the universe. They are the reason there are galaxies, the reason there are planets, the reason there is life. They are the storytellers of the cosmos, writing their tales in light and scattering the elements that make existence possible. When you look up at them, you are not only seeing distant suns, you are seeing the very source of life, the cosmic heartbeat that began billions of years ago and still pulses today, lighting the universe with its endless glow. When we think of the universe, our minds often turn first to stars, because they shine the brightest and dominate the night sky. Yet orbiting around those stars are billions upon billions of planets and moons, silent companions that do not blaze with light but still hold extraordinary significance. Planets and their moons are the stage upon which the drama of existence unfolds. They are where oceans form, where atmospheres evolve, where mountains rise and winds blow, and, at least in one special case, where life emerges. The diversity of these worlds is staggering, far beyond what we once imagined, and each one offers a unique story about how the universe works. Our journey of understanding began, of course, with our own solar system. For most of human history, it was believed to be the center of everything. The sun, moon, and planets were thought to circle us in perfect harmony. Over time, we learned that Earth itself is a planet, orbiting a star that is just one of countless others. That realization was profound. It meant that our world was not unique in being a planet. And if Earth is a planet circling a star, then surely countless other planets must exist across the cosmos. Today, with powerful telescopes and advanced detection methods, astronomers have confirmed this suspicion. We now know of thousands of exoplanet planets orbiting stars beyond our sun, and the number continues to grow with every passing year. Even within our solar system, the variety of planets is astonishing. We have the inner rocky worlds Mercury, Venus, Earth, and Mars, each with its own character. Mercury is a scorched and cratered landscape, closest to the sun and with almost no atmosphere to shield it. Venus, by contrast, is shrouded in thick clouds of carbon dioxide, trapping heat in a runaway greenhouse effect that raises surface temperatures high enough to melt lead. Mars, with its rusty deserts, massive volcanoes, and frozen polar caps, has long intrigued us as a possible home for life in the past, and perhaps even now, beneath its surface. And Earth, our blue planet, is the jewel of them all. A world where liquid water flows, where the atmosphere sustains life, and where countless ecosystems thrive. Farther out lie the gas giants, Jupiter and Saturn, immense worlds composed mostly of hydrogen and helium. Jupiter, the largest planet in our solar system, is a swirling giant with storms larger than Earth itself, including the Great Red Spot, a tempest that has raged for centuries. Saturn, with its stunning rings made of ice and rock, is one of the most visually striking objects in the night sky, a reminder that beauty in the universe often comes in unexpected forms. Beyond them are the ice giants Uranus and Neptune, with their blue-green hues caused by methane in their atmospheres, and their mysterious internal structures that remain largely unknown. But planets are not alone. Many are accompanied by moons, and moons themselves can be worlds of wonder. Our own moon, with its craters and seas of basalt, has been Earth's companion for billions of years, shaping tides and stabilizing our planet's tilt. Yet the moons of other planets are just as fascinating, if not more so. Jupiter's moon Europa hides a vast ocean beneath its icy crust, an ocean that may contain more water than all of Earth's combined. Saturn's moon Titan has lakes and rivers of liquid methane and ethane, a landscape that in some ways mirrors Earth's but with entirely different chemistry. Enceladus, another moon of Saturn, spews geysers of water vapor into space, hinting at an ocean below its surface. These icy moons may be some of the most promising places to search for life beyond Earth. The diversity of planets and moons extends even further when we consider exoplanet Some orbit their stars at just the right distance for liquid water to exist the so-called habitable zone, while others hug their stars so closely that they are scorched and tidally locked, with one side in eternal daylight and the other in endless night. Some exoplanets are massive gas giants orbiting closer to their stars than Mercury does to the Sun, earning the nickname hot Jupiters. Others are rocky super-Earths, larger than our planet but smaller than Neptune, with unknown atmospheres and climates. Every discovery stretches our imagination, revealing possibilities we never thought could exist. What makes planets and moons so captivating is that they represent the potential for places like our own. Stars are magnificent, but they are not where life dwells. It is on the surfaces of planets and moons, in their oceans, in their atmospheres, and in their soils, that the conditions for life may arise. The search for extraterrestrial life is therefore closely tied to the study of worlds. Every time astronomers detect an exoplanet in the habitable zone of its star, it sparks the question, could this place harbor life? Could there be oceans beneath its clouds, forests under its skies, or even civilizations gazing back at us across the gulf of space? The sheer number of planets is staggering. Based on current estimates, there may be more planets in the universe than stars. Our Milky Way alone, with its hundreds of billions of stars, likely contains hundreds of billions of planets. If even a small fraction of them are Earth-like, the number of potentially habitable worlds becomes mind-boggling. In that context, Earth begins to feel both incredibly special and humblingly ordinary. Special, because it is our home, the only place we know for certain that life exists. Ordinary, because it is one planet among countless others, part of a cosmic tapestry so vast we can barely comprehend it. Moons, too, remind us that worlds need not orbit stars to be intriguing. Some moons may have subsurface oceans kept warm not by sunlight, but by tidal heating, the gravitational stretching and flexing caused by their parent planets. In these hidden oceans, shielded from the vacuum of space, life could quietly flourish, completely independent of starlight. This idea expands our understanding of habitability, showing that life might not be restricted to Earth-like planets in habitable zones. It might emerge in the most unexpected corners of the cosmos. The study of planets and moons is not only about curiosity, it is also about perspective. By comparing Earth to other worlds, we learn more about our own. Venus teaches us about the power of greenhouse gases. Mars reminds us how fragile atmospheres can be. Europa and Enceladus show us that water can exist in abundance, even far from the warmth of a star. Each world is like a natural laboratory, offering lessons that deepen our understanding of planetary science, climate, and the conditions necessary for life. In recent decades, spacecraft have allowed us to see these worlds up close. The Voyager probes, launched in the 1970s, gave us our first detailed glimpses of the outer planets and their moons, revealing landscapes more exotic than anything we imagine. The Cassini mission spent over a decade exploring Saturn, sending back breathtaking images of its rings and uncovering the secrets of Titan and Enceladus. Rovers on Mars have traversed its dusty plains, drilling into rocks, searching for signs of ancient water, and preparing the way for possible human exploration. These missions remind us that planets and moons are not distant abstractions, they are real places, tangible and waiting to be explored. When we look at the diversity of planets and moons, what emerges is a picture of abundance. The universe is not stingy in its creation of worlds. It is prolific, scattering planets and moons like seeds across the galaxy. Each one is unique, shaped by its distance from its star, by its size and composition, by the history of impacts and migrations that sculpted its surface. Some are hot and stormy, others icy and serene. Some may be barren forever, while others may carry the spark of life. Together, they form a gallery of possibilities, a reminder that the cosmos is filled with more worlds than we could ever visit, more than we could ever dream. In the quiet of night, when the stars shine above us like distant lanterns, it is easy to imagine the universe as a peaceful place, calm and steady, filled with gentle twinkling lights. But behind that serene image lies something far more extreme: objects so dense, so powerful, and so mysterious that they stretch the very fabric of reality. These are black holes and neutron stars, cosmic remnants born from the violent deaths of massive stars. They do not simply exist within the universe. They bend it, twist it, and remind us of nature's incredible extremes. To understand these objects, we must return to the life of a massive star. Unlike our sun, which will one day end gently as a white dwarf, massive stars, those at least 8 times the mass of our sun, live fast and die dramatically. Their cores burn through fuel quickly, creating heavier and heavier elements until iron forms at their center. Iron cannot release energy through fusion, and when the star can no longer produce outward pressure to balance gravity, the core collapses in an instant. The result is a cataclysmic explosion known as a supernova, one of the most powerful events in the universe. What remains after this explosion depends on the mass of the collapsed core. If it is between about 1 and 3 times the mass of the sun, it becomes a neutron star. If it is greater, gravity crushes the matter so completely that nothing can stop its collapse, forming a black hole. These two fates, neutron stars and black holes, represent the universe at its most extreme. Where the ordinary rules of physics give way to something stranger, neutron stars are among the densest objects in existence. Imagine compressing the sun into a sphere only about 12 miles across, roughly the size of a city. That is a neutron star. The gravity on its surface is so immense that a single teaspoon of its material would weigh billions of tons on Earth. Inside, matter is crushed to the point that atoms themselves break down, leaving behind a sea of neutrons packed tightly together. This is matter in its most extreme state, a kind of cosmic nuclear soup. Despite their tiny size, neutron stars are incredibly powerful. Many spin rapidly, sometimes hundreds of times per second, beaming radiation out into space like a cosmic lighthouse. These objects are called pulsars, and their precise pulses of light allow astronomers to study them with extraordinary detail. Some pulsars are so stable that their timing rivals atomic clocks, making them valuable tools for studying gravity, space-time, and even detecting the faint ripples of gravitational waves across the cosmos. Then there are magnetars, a rare type of neutron star with magnetic fields, trillions of times stronger than Earth's. These magnetic fields are so powerful that they could strip information from a credit card if you were somehow able to bring one close enough. Magnetars occasionally release bursts of high-energy radiation so intense that they can be detected from across the galaxy. They are living reminders of how strange and unpredictable the universe can be. If neutron stars are extreme, black holes are the very edge of possibility. A black hole forms when gravity wins completely, collapsing matter into a point of infinite density called a singularity. Surrounding the singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. Once something crosses that invisible line, it is lost forever, swallowed into the depths of the black hole. From the outside, a black hole appears as a dark sphere, a hole in the fabric of space-time itself. The idea of black holes may sound like science fiction, but they are very real. Astronomers have found evidence for black holes across the universe, from stellar mass black holes a few times the mass of our sun, to supermassive black holes millions or billions of times heavier, lurking at the centers of galaxies. In fact, at the center of our own Milky Way lies a supermassive black hole called Sagittarius A, with a mass equivalent to 4 million suns. For decades, it was only suspected, but in 2022, scientists captured the first direct image of its shadow, using a planet-sized network of telescopes called the Event Horizon Telescope. The result was a blurry but unmistakable glimpse into one of the greatest mysteries of existence. Black holes are not simply hungry monsters that devour matter. They are also engines of energy. When gas and dust spiral into a black hole, they form an accretion disk, heating up to millions of degrees and emitting powerful radiation. Some black holes launch jets of particles at nearly the speed of light, extending for thousands of light years into space. These jets shape galaxies, influence star formation, and play a central role in the evolution of cosmic structures. What happens inside a black hole remains one of the greatest questions in physics. At the singularity, the laws of physics as we know them break down. General relativity, which describes gravity on large scales, collides with quantum mechanics, which governs the very small. Somewhere in that clash may lie the key to a deeper theory of everything, a framework that unites the forces of nature. For now, black holes are both laboratories and mysteries, testing the limits of our knowledge. One of the most extraordinary discoveries of recent years has been the detection of gravitational waves ripples in space-time predicted by Einstein more than a century ago. In 2015, the LIGO Observatory detected these waves for the first time, caused by the collision of two black holes over 1 billion light-years away. The signal was faint, but it marked a revolution in astronomy, opening a new way of observing the universe. Since then, astronomers have detected dozens of gravitational wave events, including neutron star mergers that produced both gravitational waves and light. These discoveries show us that the universe is not silent, it vibrates, it ripples, and we can now listen to its faintest echoes. Neutron star collisions are especially fascinating. When two neutron stars spiral together and merge, they unleash colossal amounts of energy, producing heavy elements like gold and platinum in the process. In fact, much of the gold on Earth was likely created in such cataclysmic events billions of years ago, before our solar system formed. The jewelry we wear, the circuits in our electronics, the metals in our technology all may trace their origins to the violent collision of neutron stars far across the galaxy. The study of black holes and neutron stars also pushes us to reconsider our place in the universe. These objects remind us that the cosmos is not made for human comfort. It contains environments of unimaginable extreme surfaces where matter is crushed beyond recognition, regions where time slows to a crawl, places where light itself cannot escape. And yet, from Earth, we can study them, measure their effects, and even capture their images. Our ability to understand these cosmic monsters is a triumph of human curiosity and perseverance. Even in their darkness, black holes and neutron stars illuminate the universe with meaning. They are the graves of stars, but also the birthplaces of new elements. They represent destruction, but also creation. They are the universe showing us that its laws can lead to both chaos and order, to both beauty and terror. When we study them, we are not just learning about distant objects. We are peering into the very fabric of reality, testing the boundaries of what is possible. And when you look up at the night sky, dotted with stars that seem eternal, remember that hidden among them are these silent mysteries. Black holes and neutron stars are invisible to the naked eye, yet they shape galaxies, sculpt matter, and hold the secrets of the universe itself. When we gaze into the night sky, the question almost asks itself. With billions of stars stretching across the heavens, each one potentially hosting its own system of planets, it feels nearly impossible to believe that Earth is the only world to harbor life. Yet for all of our searching, all of our listening, and all of our exploring, we have yet to confirm a single example of life beyond our pale blue dot. The question of whether we are alone in the universe is one of the most profound mysteries humanity has ever faced. And it brings together science, philosophy, and imagination in equal measure. Life on Earth offers us the only example we know for certain, so it is the natural place to begin. Here is astonishingly resilient, able to adapt to environments once thought impossible. On the ocean floor, in darkness so deep no sunlight has ever reached, microbes cluster around hydrothermal vents, drawing energy not from the sun, but from chemical reactions. In deserts, bacteria survive in rocks, clinging to existence where water is almost absent. In the icy reaches of Antarctica, tiny organisms endure freezing temperatures, high radiation, and little food. These extremophiles show us that life does not require gentle conditions, it finds a way in extremes. This adaptability opens our imagination to what might be possible elsewhere. If life can thrive in boiling acid pools or in sub-zero glaciers on Earth, then perhaps it could exist beneath the frozen crust of Europa, one of Jupiter's moons, where a vast subsurface ocean sloshes in darkness, warmed by tidal forces. Or perhaps on Enceladus, a moon of Saturn, where geysers shoot water vapor into space, hinting at a hidden ocean rich with organic chemistry. Mars, though dry and barren today, once had rivers, lakes, and perhaps even oceans. Some scientists believe it still hides microbial life underground, protected from radiation by layers of rock, but the search does not end in our solar system. With the discovery of thousands of exoplanet orbiting distant stars, the possibility of Earth-like worlds has moved from speculation to observation. Astronomers use techniques like the transit method, watching as a planet passes in front of its star, causing a tiny dip in light. This allows them to estimate the planet's size, orbit, and sometimes even its atmosphere. Many of these worlds orbit within the so-called habitable zone, the distance from their star where liquid water could exist. Some are rocky, like Earth, raising tantalizing questions about whether they might support life. The search for life also extends to the chemical fingerprints of biology. Scientists examine exoplanet atmospheres for biosignatures, gases like oxygen, methane, or combinations that are difficult to explain without life. On Earth, for instance, our atmosphere is rich in oxygen because plants and algae produce it through photosynthesis. Without life, oxygen would quickly react away. Finding a similar imbalance in another planet's atmosphere would be a powerful clue that something alive might be at work, yet life elsewhere may not look anything like life here. The biology we know is based on carbon, water, and DNA, but in the vastness of the cosmos, other chemistries may be possible. Perhaps there are life forms built on silicon instead of carbon, or organisms that use liquid methane instead of water as their solvent. Like the lakes and seas found on Saturn's moon Titan, life could be microscopic, spread through vast numbers across galaxies. Or it could take forms we cannot yet imagine, hidden from us simply because we do not know how to recognize it. The search for intelligent life adds another layer of mystery. For decades, scientists have listened to the skies through projects like SETI, the search for extraterrestrial intelligence, hoping to catch a signal, a deliberate transmission from another civilization. So far, the silence has been unbroken, a phenomenon often called the Fermi paradox. If the universe is so vast and old, and if intelligent life is not unique to Earth, then why have we not seen any evidence of it? Some suggest that civilizations may be rare, short-lived, or too far apart to communicate. Others propose that we are listening with the wrong tools, or that advanced civilizations may not use radio waves at all. The possibilities stretch from sobering to exhilarating. Perhaps we truly are alone, a rare spark in an otherwise lifeless universe. If so, the responsibility of protecting and cherishing life on Earth becomes even greater, for it may be the only example of its kind. Or perhaps life is common, scattered like seeds across galaxies, waiting for us to find it. That discovery would change everything, reshaping how we see ourselves and our place in the cosmos. Even the idea of microbial life elsewhere would be revolutionary. Finding bacteria beneath the ice of Europa or fossils on Mars would prove that life is not unique to Earth. It would suggest that wherever conditions are right, life emerges naturally, as if the universe itself longs to bring it forth. And if life can start twice in one solar system, then it might be everywhere in countless worlds orbiting countless stars. Some scientists propose the concept of panspermia, the idea that life spreads from one planet to another, carried on asteroids or comets. In this view, Earth's life may not have started here at all, but may have arrived from elsewhere, seeded from the stars. If true, it would connect us directly to a cosmic story of life traveling across space, surviving impacts, and taking root on worlds whenever it finds the chance. At the heart of this exploration lies a deep human curiosity. We ask if we are alone, just for scientific reasons, but for emotional and philosophical ones. Knowing whether we share the universe with others would transform how we see ourselves. If we are alone, then humanity carries a singular weight, the only beings capable of wonder, thought, and exploration. If we are not, then we are part of a greater community of life, one branch of a cosmic family tree. Every discovery we make brings us closer to answers. Each exoplanet catalogued, each icy moon explored, each new signal searched adds to the mosaic of possibility. Though we have not yet found life beyond Earth, the search itself is part of the wonder. It teaches us about resilience, about chemistry, about the diversity of worlds, and the adaptability of existence. It reminds us that life is not just a scientific phenomenon, it is a miracle of persistence, of transformation, of the survival against all odds. As you drift deeper into thought, picture the countless stars overhead, each one a sun, each one a possibility. Imagine the world spinning around them, some barren, some icy, some hot and hostile, but perhaps some alive, with forests, oceans, or creatures we cannot imagine. Perhaps even now, on some faraway planet, another being is looking up at its own sky, wondering the same thing. Are we alone? When we look at the night sky, we are peering not just across vast distances of space, but also across the deep gulf of time. The light of distant galaxies has traveled for millions or even billions of years before reaching our eyes. In this way, astronomy is a kind of time machine, revealing the story of the cosmos in slow motion. We see galaxies as they were long ago, stars that may have already burned out, and cosmic structures that have evolved over eons. This naturally leads to a question as profound as it is unsettling: what comes next? If the universe has a past and a present, then it must also have a future. And the fate of everything, galaxies, stars, planets, and even life itself, depends on how the story unfolds. To begin to understand the fate of the universe, we must look back to its beginning. The Big Bang set everything in motion nearly 13.8 billion years ago, and ever since, the universe has been expanding. For much of human history, people imagined the universe as static and eternal, but in the 20th century, observations revealed otherwise. Galaxies are racing away from one another. Space itself is stretching, and the expansion is accelerating, driven by a mysterious force called dark energy. The ultimate destiny of the universe is tied to this expansion, to the battle between gravity, which tries to pull matter together, and dark energy, which pushes everything apart. One possible future is the so-called heat death of the universe, sometimes referred to as the Big Freeze. In this scenario, expansion continues forever, and galaxies grow farther and farther apart until they vanish beyond one another's horizons. Stars will eventually exhaust their fuel, fading into white dwarfs, neutron stars, and black holes. Over unimaginable timescales, even these remnants will cool, evaporate, or decay. The universe will become dark and cold, filled only with thin gas and the fading radiation of long-extinguished stars. Entropy, the measure of disorder, will reach its maximum, and the cosmos will become a vast, silent expanse where no new structures can form and no life can survive. The timescales involved in this scenario stretch the imagination. Stars like our sun will last billions of years, but once the last red dwarf's tiny, long-lived stars burn out after trillions of years, there will be no new light. Black holes themselves will persist far longer, but even they are not eternal. According to Stephen Hawking's theory of Hawking radiation, black holes slowly evaporate over time, releasing energy in the process. A small black hole might evaporate quickly, but a supermassive black hole at the center of a galaxy will take 10,100 years or more to vanish, a number so vast it defies comprehension. Eventually, even they will be gone, leaving only darkness. Another possibility is the Big Rip. If dark energy does not remain constant, but instead grows stronger over time, the acceleration of the universe could increase without limit. In this scenario, galaxies would first drift apart, then stars within galaxies would be torn from one another, then planets from their stars, and eventually even atoms themselves would be ripped apart as the very fabric of space-time stretches to infinity. The Big Rip envisions a universe that ends in violence, shredded by its own expansion in a catastrophic finale. The timing of such an event depends on the properties of dark energy, which remain one of the greatest mysteries in physics. Alternatively, the universe might one day reverse its course in what is called the Big Crunch. In this scenario, expansion eventually slows and halts, giving way to contraction. Galaxies would begin to move toward one another, stars would collide, and the universe would collapse into an incredibly dense state, possibly ending as it began, in a hot, dense singularity. Some theories suggest that this collapse could lead to another Big Bang, creating a cyclic universe that expands, contracts, and is reborn endlessly. This cosmic rebirth offers a vision of eternal renewal, though it is less favored by current observations, which suggest expansion is accelerating, not slowing. There are also more speculative possibilities. Some physicists imagine a scenario known as vacuum decay, in which the universe is not in a perfectly stable state, but rather a metastable one. In this case, a quantum fluctuation could trigger a bubble of lower energy vacuum that would expand at the speed of light, rewriting the laws of physics as it consumed everything in its path. This catastrophic possibility is almost impossible to predict, but it reminds us that our universe is governed by deep physical laws we are only beginning to understand. Whichever path the universe follows, time itself becomes a central character in this story. Human lives are brief in cosmic terms, mere moments in a universe billions of years old. Even the lifespan of stars is tiny compared to the projected lifespans of black holes or the endless trillions of years that stretch ahead. To contemplate the fate of the universe is to confront time on scales so vast that ordinary language falters. We speak of trillions, quadrillions, and numbers with more zeros than we can imagine, and still they fall short of the cosmic reality. Yet within this immensity lies a profound sense of wonder. The fact that we can even ask these questions, that human beings on a small planet can imagine the end of everything, is a testament to our curiosity. It may be that the universe will end in darkness, but in the meantime life exists. Stars burn, galaxies spin, and consciousness looks out upon the cosmos and dares to ask how it will all unfold. The fate of the universe may be sealed, but the meaning we draw from it is ours to shape. There is also comfort in the knowledge that whatever the future holds, it will unfold on scales of time so vast that they do not threaten our present. Whether the universe ends in heat, death, rip, crunch, or something stranger, these events lie far beyond the lifespan of stars, galaxies, and even atoms as we know them. For us, the universe is young, vibrant, and full of possibility. We live at a moment when stars still shine, galaxies still cluster, and life can emerge. We are part of a cosmos in its prime. The study of the universe's fate also inspires humility. We are small creatures on a fragile planet, yet we are capable of asking questions that stretch to infinity. The stars we see tonight will still shine for millions of years, and yet we can imagine their deaths, and beyond that, the silence of eternity. In thinking about the future of the cosmos, we confront not only physics, but also philosophy, grappling with the nature of existence and our place within it. As you lie back and picture the stars overhead, imagine them as part of a grand story still unfolding. Each galaxy is a character in a narrative that stretches across time, each star a fleeting spark, each world a possibility. The universe is vast, mysterious, and destined for change. And though we cannot yet know the ending, we can marvel at the beauty of the journey, at the cosmic dance that began billions of years ago and will continue long after we are gone. From the moment early humans first looked up at the night sky, filled with glittering stars and a silver moon, questions began to stir in the human mind. What are those lights? Why are they there? What lies beyond them? Curiosity has always been woven into our existence, driving us to seek answers and shaping the story of our species. And as we sit here now, in a modern age of telescopes, space probes, and satellites, the questions remain as alive as ever, echoing the ancient wonder of those who first tilted their heads skyward. Human curiosity is unlike anything else we know in nature. It pushes us beyond survival, beyond the need to eat, drink, or find shelter. It compels us to explore for the sake of knowing, for the joy of understanding something larger than ourselves. This thirst for knowledge has carried us from the caves of our ancestors to the vast reaches of space. It is a force as old as humanity itself, and in many ways, it defines who we are. Place in the cosmos is both humbling and inspiring. On one hand, we are small tiny beings on a planet that is itself a speck in a solar system, which is just one of billions within our galaxy, which is just one among trillions of galaxies spread across the observable universe. If the cosmos were a vast ocean, Earth would be a grain of sand on an endless shore. Yet at the same time, we are the universe made conscious, the only known life capable of asking questions about its origins and its destiny. In us, the universe reflects upon itself. Science has been our tool for turning curiosity into knowledge. Over centuries, we have learned that stars are not tiny pinpricks of light, but enormous suns burning across unimaginable distances. We have learned that planets circle those stars, and that galaxies stretch into the deep beyond. We have discovered black holes, cosmic background radiation, the structure of DNA, and the expansion of space itself. Each discovery has reshaped our view of reality, sometimes shrinking us in scale, but always expanding our sense of wonder. Consider how far curiosity has taken us in just a short span of time. Barely more than a century ago, powered flight was only a dream, and the idea of reaching space was a fantasy. Yet today, we have walked on the moon, sent rovers to Mars, and launched probes that have left the solar system entirely. Voyager 1, launched in 1977, now drifts through interstellar space, carrying with it the golden record, a message from humanity etched in sound and image, a time capsule of who we are, traveling among the stars. This act alone is a pure expression of curiosity and hope, the desire not only to explore, but also to be known, to declare that we were here. Curiosity also drives us inward. Just as we look outward to the stars, we also peer into the smallest building blocks of matter, exploring atoms, particles, and the quantum fabric of reality. We investigate the origins of life, the workings of the brain, and the mysteries of consciousness itself. The same spark that once led a child to ask why the sky is blue now drives scientists to ask why the universe exists at all. Our place in the cosmos is not simply defined by where we are, but by how we think, how we dream, and how we explore. We are participants in a cosmic story far larger than ourselves, yet we are also storytellers, weaving meaning into what we see. The universe does not ask to be understood, but we ask anyway. The universe does not speak, but through mathematics, physics, and observation, we have learned to listen. There is a paradox at the heart of this journey. The more we learn, the more we realize how little we know. Every discovery opens new questions. When we found that the universe is expanding, we wondered what drives it, and we uncovered the mystery of dark energy. When we mapped galaxies, we realized their visible matter is only a fraction of what exists, and we met the enigma of dark matter. When we studied black holes, we found contradictions between relativity and quantum mechanics. Each answer is a doorway, each insight an invitation to look deeper. But curiosity is not only about science. It also shapes our imagination, our art, and our culture. It drives us to write myths and legends about the stars, to compose music inspired by the heavens, to paint the swirling galaxies we cannot yet see. Long before telescopes, humanity told stories of Orion, Cassiopeia, and the Milky Way. Today, even as science explains the mechanics of the cosmos, those stories remain, reminding us that curiosity is also about meaning, about connection, about placing ourselves within the universe in ways both rational and emotional. Our place in the cosmos is also one of responsibility. If life is rare, if Earth is the only cradle of consciousness, then we bear a weight unlike any other: the responsibility to preserve, to protect, and to continue the miracle of life. Our curiosity compels us to search for other worlds, but it also reminds us of the fragile beauty of our own. The pale blue dot, as Carl Sagan described it, holds everything we know and love, and it floats in a vast dark sea. To explore the universe is also to cherish this small world, to recognize how precious and irreplaceable it is. Looking to the future, curiosity will guide us further still. We will return to the moon, set foot on Mars, and send new probes to the icy moons where oceans may hide. We will build more powerful telescopes to peer at the atmospheres of distant planets, searching for signs of life. We will probe deeper into the mysteries of dark matter and dark energy, seeking the invisible scaffolding of the cosmos. We will continue to listen for signals from other civilizations, wondering if someone else out there is also gazing up at the stars, asking the same questions. Yet even if we never find definitive answers, the journey itself matters. The act of seeking, of wondering, part of what makes us human. Curiosity shapes our identities, binding generations together in a chain of inquiry that stretches from ancient stargazers to modern scientists and beyond. Our place in the cosmos may be small in scale, but it is vast in meaning, because we are not just passive observers. We are active participants, asking questions, telling stories, and imagining futures. As you close your eyes and imagine the night sky, picture yourself as part of this great unfolding story. You are not separate from the universe, you are a piece of it, made of the same elements forged in the hearts of stars. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were born in ancient stellar furnaces and scattered across space by supernova. When you look up at the stars, you are looking at your own history, your own origin, written across the heavens. And so our curiosity continues, as endless as the cosmos itself. It carries us outward, inward, forward, and beyond, reminding us that our place in the universe is not defined by size or power, but by wonder, by imagination, and by the unshakable desire to know. As we have drifted together through this vast journey, we have explored beginnings and endings, mysteries and certainties, questions and possibilities. We began with the Big Bang, the spark that set time and space into motion, and followed the unfolding story of galaxies and stars, of planets and moons, of black holes and neutron stars that stretch the very fabric of reality. We paused to wonder about life beyond Earth, to ask the age-old question of whether we are alone, and we considered the possible destinies awaiting the cosmos itself. Through it all, we found ourselves returning to the same truth, that our curiosity is what ties us to the stars, that our smallness does not diminish us, but deepens our place in the story. The universe is vast beyond measure, filled with mysteries we cannot yet solve, and distances we cannot yet travel. Yet here we are in this fragile blue world, able to imagine it all. The iron in our blood was forged in ancient stars. The molecules that form our bodies are part of a cosmic cycle billions of years in the making, and our minds, delicate yet powerful, are capable of gazing into infinity and asking what comes next, whether the universe ends in silence or renewal, whether life is rare or common, whether we ever find companions among the stars. The act of wondering binds us together across generations. It is what makes us explorers, dreamers, and storytellers. To lie beneath the night sky and let your thoughts stretch outward is to be fully human. To feel both the humility of our scale and the grandeur of our imagination. So, as you settle deeper into rest, carry with you the calm of knowing that you are part of this vast and beautiful cosmos. You are made of its matter, shaped by its forces, and guided by the same curiosity that has always drawn humanity to the stars. The universe is immense, mysterious, and still unfolding, and in its story, you too have a place.